Hi everyone. Thank you for coming to our third summer colloquium. Our speaker today is Dr. Charlie Conroy. Dr. Conroy is an expert on galaxy evolution and stellar population synthesis modeling. Dr. Conroy got his PhD from Princeton in 2010, and then he came here as a postdoc and left for UC Santa Cruz, nicer weather, kind of hotter, for 2 years as a faculty member, and then returned to the CfA and has been here for just about a year now, right? So without any further ado, please welcome Dr. Charlie.
All right, thanks for coming. Hold on a second. Right, so today I wanted to talk a little bit about the things that I work on and that the folks in our group work on. The title of the talk I normally give is Extragalactic Archaeology, which is kind of a fancy, fun-sounding buzzword. The basic idea is we want to use the properties of the stars and galaxies to learn about the histories of galaxies. So it's like archaeology of the stars. Just a little background before I get started. In terms of my trajectory, I started out as on the sort of more observational side as an undergraduate at Berkeley. I was working with Mark Davis on the Deep 2 redshift survey, so we were doing sort of galaxy formation cosmology. As a graduate student, I started working more on stellar populations and some of the more sort of background theory there. And then since then, I keep drilling down to smaller and smaller scales, working on stars, stellar spectra, stellar evolution, because it turns out that to understand galaxies and large-scale structure and how galaxies assemble, we have to understand the stars within them. And there are interesting unsolved problems in the fields of stellar evolution and stellar spectroscopy. So we've been trying to branch out into more and more fields as we go along. So some of the big overarching questions, this is going to be, there's a lot of introduction here to get everybody on the same page. Some of the big basic questions in the fields of galaxy formation and galaxy evolution at a very fundamental level are why did the universe produce these two types of galaxies as opposed to, say, only one type or many types? To a good approximation, there is a very strong bimodality in the properties of galaxies. They don't sort of span a continuous range of properties. They tend to cluster around things that look like these elliptical galaxies on the left-hand side. Pretty spherical and red-like to the eye, and then galaxies that look more like the Milky Way, these grand, beautiful spirals that have these dust lanes, and they look kind of more blue to the eye. So, this is one of the overarching questions in the field. We don't have a good answer to it, but an even more basic question that you might ask is why does this galaxy look red and this galaxy look blue? And the answer, of course, has to do with the kinds of stars that are in those galaxies. So even just looking in a very crude sense at the colors, you can get a sense of this galaxy contains a lot of blue stars, and blue stars are hot and young. This galaxy contains only red stars, and red stars tend to be older. So already just by looking at the colors, you can get some sense of what's going on in the galaxies. Another broad question is how do we go from the high redshift universe, where galaxies were at one point in their lives, to the present day universe, where you see galaxies today? It turns out that at the present epoch, galaxies obey, in each one of these two categories, they obey remarkably uniform relations of various kinds with very little intrinsic scatter. So the relations between the mass of the galaxy, its metallicity, its star formation rate, its size, all these relations are very tight with very small scatter. And that's kind of a surprise given what we think we know about the assembly history of galaxies in the universe. We think we live in a universe dominated by cold dark matter. And if people run simulations that involve sort of prescriptions for how dark matter forms and assembles. And there are these things that we call dark matter merger trees, where you start at high redshift, and there's all these little tiny lumps of dark matter. And over time, those lumps assemble, and they merge together. And so time is going in this direction. And as you go later and later in time, all these little clumps assemble, and they merge together. And it's really kind of a remarkably violent process. And so it's somewhat remarkable that in light of all this violence that happens in the universe, you end up at the end of the day with these very uniform and simple things. So to make that a little bit more visually striking, many of you have probably seen movies like this before, but I'll just show an obligatory one here. This is the a simulation of only dark matter. It's called the Aquarius Simulation. It's supposed to be a region of the universe that looks like where we live in the Milky Way. It starts at very high redshift. The color coding is density. You're moving around this structure. The universe isn't actually spinning. This is only dark matter. There's no gas. There's no stars. It started out with initial conditions that we think were set by inflation and that are constrained by the cosmic microwave background. And you see that over time, this is basically all just gravity working here, right? So the cosmic web, you see these filaments, you see these dense nodes in the cosmic web. And if you focus in on a region here, which is starting to form a denser conglomeration of dark matter, it's really just being, pummeled over and over again by the accretion of these systems. And so if you imagine, a nice little Milky Way galaxy sitting here with a very thin, cold disk of stars, how does such a uniform-looking thing emerge out of this violent history? So that's an interesting unsolved problem. You might have thought, just by looking at these simulations, that at the present epoch, you would just have a wide variety of things with no obvious, structure or correlations. But in fact, somehow the universe manages to produce a lot of structure in the face of all this chaos. So it just kind of keeps going for a while. So what are some of the big questions in the field? You might ask, well, how do we make progress observationally? And there's a handful of generic observational windows that we use to try to learn things about how galaxies form and evolve. One of the classic observational windows is known as the luminosity function, which is basically just counting galaxies as a function of how bright they are. This is one of the first attempts to do this. This is number as a function of luminosity. There's points here, and there's a curve here, which is a power law times an exponential. And this was back in the old days when you could write a power law times an exponential and have it named after you. This is now known as the Schechter function, after Paul Schechter, who multiplied those two functions together. Still used today. It's very common. But it's a basic feature that there's a power law tail at low masses, and then as you go to higher masses or higher luminosities, there's this cutoff, this exponential cutoff. So people have measured this as a function of different wave bands, from the blue to the infrared and the ultraviolet, and as a function of redshift, and have used this to learn a lot about how galaxies grow over time. It turns out it's actually difficult in practice to measure the total luminosity of the galaxies because they're these extended fluffy things, but anyways, people try. More recently, people have gotten much more bold, and rather than just simply measuring luminosities, they've tried to interpret those luminosities with models and measure things such as the stellar mass in the galaxy or the star formation rate of the galaxy. This is what we'll spend more time talking about in a few minutes, but these results, as you might imagine, are very model dependent. Despite this, the community has sort of all drunk in the Kool-Aid, and they almost never even show luminosity functions from a given survey of galaxies. They typically will take the luminosities, run them through a sophisticated code, and just produce things like this, which is the mass function. This is intuitively more interesting and more interpretable, if you can believe these models, because this is actually something you might compare to a simulation or to some analytic models for how galaxies assemble. But it is much more model dependent. Another broad class of observational windows would be the structural properties of a galaxy. Rather than treating the galaxy as just a point of light, you analyze and quantify the structure. So galaxies, some look like this. They're sort of long cigar-shaped things. You can look at the light profile. This is the surface brightness as a function of radius. So they have they are peaked in surface brightness in the middle region. Some have this. They have all these funny bumps and wiggles and different profiles at large radius. So the whole two-dimensional light profile contains a lot of important information about how galaxies form and assemble. And what we'll focus on mostly here is what I would call medium resolution spectra. So actually taking the light and spreading it out as a function of wavelength. And that gives you a huge and rich array of information about the stars and galaxies. In principle, you can learn about the ages of the stellar populations, the metal patterns, so carbon, nitrogen, oxygen, iron abundances, the stellar initial mass function, which I'll explain in a minute, the whole history of star formation, the metallicity in the gas. There's a huge amount of diagnostics that you can learn if you can actually start to pull apart the spectra of galaxies. This is an example of a model of one of those old red-looking galaxies. All these features here are actually atomic and molecular absorption features. So this is not noise, this is all actual information encoded here. So the goal is to build models that can extract that kind of information. One more sort of summary slide about what galaxies, what's going on and why they're complicated. Galaxies are this kind of interesting node of many different physical processes. On the one hand, you have the evolution of the universe as a whole, which is determining the large-scale distribution of galaxies in the universe. You have the evolution of dark matter, which, as I showed you in the movie a few minutes ago, is controlling what kinds of galaxies merge together. You have, of course, star formation, so galaxies form stars over time, and that's what makes them look the way they do in the optical. You have stellar evolution, so once those stars form, certain stars evolve and die. So the high-mass stars live short lives and they explode. The low-mass stars live a long time. We can see them for a long time. There's gas physics. So gas cools, gas can be heated, gas can flow out of the galaxy or flow into the galaxy, so that all has to be modeled. There's this generic term, this buzzword that's called feedback. The basic idea is that, for example, when stars form, more massive stars will explode as supernova. They might inject energy into the surrounding gas, which might then turn off subsequent star formation. So it's a negative feedback loop. We think there are a variety of these feedback loops that happen in galaxies, but we really don't understand how they work in detail. We believe most galaxies have a gigantic black hole at the center, and they probably have an interesting level of influence on the formation of the galaxy and its star formation and so on. And again, as I said, galaxies can collide and interact, and that can shape how galaxies look. We think that those red-looking spherical galaxies are the result of galaxy collisions, and et cetera. So there's, all these things come together. Everything from stars and stellar evolution to gas physics to dark matter and cosmology all have to come together, and that's how we get galaxies out at the end of the day. So it's an exciting field to work in because it's the node of many of these different processes. So zooming in a little bit, I want to get into the question of what we can learn about galaxies from the light they emit, because there aren't very many other ways that we can learn about galaxies. We can't get in a spaceship and go into them and count their stars. We have to just take the light that they emit and learn what we can. So starting a bit schematically, this is the flux you might get from a given galaxy as a function of wavelength over a very large wavelength range. I'm not going to talk about even longer wavelengths, into the radio, or even shorter into the X-rays. I'll just stick to the UV through infrared, which is where stars tend to dominate. So this is like stellar light is dominating the optical and UV in here. These broad emission lines and this broad hump here are the results of dust in the galaxy. So if you want to ask the question, how do I build a model that would sort of predict all this light that's being emitted from the far ultraviolet to the far infrared? Here's what you would do. You would start with what we call simple stellar populations. The observational analog you should have in your mind is like a star cluster, so a coeval monoabundance or monometallic population. And how you would build such a population is the following. You would take stellar evolution. So that would tell you at any given age or any given time what stars are alive and what do they look like. How hot are they? How cool are they? Which ones have evolved off and died and so on. You would take stellar spectra. So at each point in this diagram, what does a star actually look like? And this can be either taken from empirical stellar libraries. People have gone out and measured spectra of hundreds and thousands of stars. Or you could do it from models, from theoretical spectral models. And then you would take the initial mass function, which is telling you the number of stars as a function of their mass at birth. This is a pretty fundamental quantity. If I take a given molecular cloud of gas and turn it into stars, the IMF specifies how many stars are born as a function of mass. And this line here that turns over, this is known as, sometimes referred to as a Krupa or a Chabrier IMF. This is what we typically observe in the Milky Way. And one of the fundamental questions is, does this fundamental IMF, does it vary at all in the universe? Does it vary with galaxy? Does it vary with star formation rate? It's an important component to this whole story. So you take these three ingredients and you fold them together, and you can predict then the light as a function of time from an integrated population. So if I took all these stars together at a given time and smushed all their light together, here's what I would see. So this is a galaxy at very young ages. It looks very hot and blue because it's got lots of hot and blue stars. And then at late times, I have a galaxy that looks a lot redder. That's this red line here. Then if I go take one more step and take these basic building blocks and add together a couple more things, if I take a star formation history, so I don't just take delta functions in time, but I allow there to be a history of star formation. I take a chemical enrichment history. So over time, a galaxy like the Milky Way will start out with very small amount of metals, basically metal-free, and it will build up those metals over time as stars explode and produce more metals. And then I have to take into account the effects of dust. So dust, these small grains of material that in the blue and optical can absorb photons and will re-emit that light into the infrared. So what's shown here is this final composite spectrum. The blue is a dust-free model, so just the effect of stars. And the red is the effect of adding dust. So it attenuates or absorbs the light in the blue and the ultraviolet and re-emits it into the infrared. All right, so this is depending on how you might view it. This is somewhat simple, but there's a lot of moving pieces. And really we want to understand, for galaxies, we want to understand things like this, the star formation rate and the chemical history. Those are sort of the fundamental things you might want to know about a galaxy. But of course, it's also clear that a galaxy spectrum depends also on these basic quantities here. So there's a really, you're learning both about stellar, basic stellar astrophysics and about the large-scale galaxy distribution at the same time. For most of this talk, I want to ignore these two ingredients, and you'll see why in a moment, and focus on these top pieces here. So depending on, your inclination, you might say, why is this so difficult? It's stellar evolution. That's simple. That's just Carolyn Ostley. Stellar spectra. That's also, what's so hard about all this? Well, this is a diagram of to give you a sense of why this is so difficult. This is very schematically age on the y-axis here and wavelength on the x-axis. So first, in this region, oh man, the colors aren't coming out at all. That's too bad. Well, just imagine like a blue little blob here behind. None of the colors are going to come out, are they? Oh, some will come. Okay, fine. So up in this upper corner here are where massive stars lie. So they're young, of course, and they're very hot, and so they emit a lot of light in the ultraviolet, in the blue. So they are very important in this part of the diagram. Now, it turns out that massive stars their evolution is not very well known. Most massive stars are in binaries. They rotate in ways we don't fully understand. They lose mass in ways we don't understand. So actually, this part of the diagram is very uncertain because we don't understand stellar evolution very well. This part of the diagram, sort of throughout the whole optical UV infrared spectrum and at young ages, there are emission lines associated with H2 regions. And those carry their own set of interesting uncertainties. And again, as I mentioned, dust absorbs light in a lot of the young to intermediate age populations in this ultraviolet and optical window. And the properties of the dust grains and how they absorb and their spatial distribution is very sensitive parameters that we don't understand very well. Similarly, in the infrared, all that dust that's absorbed is re-emitted in the infrared. And again, we don't understand a lot of these processes very well. There's a whole host of stellar types in this particular part of the diagram, in particular these asymptotic giant branch stars, also whose evolution is not very well known. And they are very important in these intermediate ages and in the near infrared. So their uncertain contribution largely affects what's happening here. And then in this part of the diagram down here, you have these another class of evolved stars called hot evolved stars, including horizontal branch stars and post-asymptotic giant branch stars. This phase is also not very well understood from first principles. Big question mark there. This is another imaginary box. For circumstellar dust, this is dust around old evolved stars. So when stars die, before they become white dwarfs, they shed a lot of their outer envelopes, and that stuff often forms dust. It can be very dusty, and how that works in detail is not well known. Okay, fine. But there's this one little sweet spot here where all these other major uncertainties are at least minimized. And this is a sweet spot that has been used for decades to model and understand galaxies. So in the optical, which is kind of a nice coincidence because that's what's easy to observe from the ground with telescopes, and for galaxies that are older than a few billion years, where many of the uncertainties associated with stellar evolution are minimized. So we'll focus on this part of the diagram for the remainder of the talk. So again, out of this whole, in principle, this rich diagnostic spectrum, we're really going to focus on this tiny little piece here. And as a way to visualize what's going on a little bit, this is a slide that I love to show. This is a model spectrum of a galaxy. It's very high signal to noise spectrum. And so if I were to zoom, there's a bunch of different features again, atomic and molecular features. If I zoom in on a chunk of the spectrum here, all these bumps and wiggles here are real features. They're all absorption features, atomic and molecular features. But this is for a model galaxy with a velocity dispersion, an internal velocity dispersion of 300 kilometers per second, which is typical for a big giant elliptical galaxy. Now, so this is just Doppler motions of the stars, sort of broadening out the spectrum. If I could, with some magical telescope, remove the Doppler motions of the stars and look at the spectrum sort of at its native resolution, as high as I could possibly observe it, this is what it would look like. So I took that one little tiny 5 angstrom chunk and blew it up to this region here and observed it at the native resolution of the photosphere of a star, which is about 1 kilometer per second. This is what you would see. So now you're looking at actually individual atomic and molecular transitions. So all this, when I look at an external galaxy, gets smoothed to this little blip here. Again, it's because of the Doppler motions of the stars. So we would love to have data like this, and certain people who study stars in the Milky Way often have access to this kind of data. It's extremely powerful. Instead, we have access to this data here. So it's a really horrible deconvolution problem that we have to work with when we're studying galaxies. So that just kind of is a visual impression of what's going on. So to give you a sense, again, kind of the diagnostic power of the spectra, this is a library of actual empirical stars, spectra of stars, in the red spectral range, so about 8,000 angstroms. And just a whole bunch of different spectral types. So this is F3 dwarf star, this is a warm star, these are cooler stars, this is like the sun here, and this is even cooler stars. And so you see all these different fascinating features that are labeled. There's hydrogen lines, there's calcium and aluminum, magnesium. As you go redward, you see these deep bands here. These are titanium oxide molecular features. So in principle, right, all of these features are telling you something about the abundance of the atoms in these stars. And so it'd be kind of interesting to learn about them. And I'll explain in a minute why you might care to measure those things. In addition, and this is something that's been known for a long, long time, for stars, even for the same temperature, spectral features can depend very sensitively on the luminosity of the star, basically. So for two stars at the same temperature, this is a star that's a dwarf star, so kind of like a sun-type star, but lower mass. And these lines up here are giant stars, so big giant stars, very large in radius. And they have roughly the same temperature, but they have very different strengths of these particular features here. And this is what people have argued or proposed can be used to actually measure the initial mass function in other galaxies. Because these features here are sort of unique fingerprints to the presence of these dwarf stars. So even though these low mass stars might only contribute a few % of the light, they have these unique fingerprints that should allow you to see their presence in distant galaxies. So they're often referred to as surface gravity sensitive features. They allow you to separate the dwarfs from the giants in other galaxies. So again, as I mentioned, stellar evolution comes into play because it tells you which stars are alive at a given time. So for early ages, you have very bright and very hot stars, and at late times you have just the cooler stars, and they're less luminous. And so that'll affect, of course, the overall shape of the spectrum. This is what you would get at the end of the day, an integrated spectrum of a galaxy at old ages. The first thing you can imagine doing is asking, how does a spectrum change if I change the age of the population? That's what's shown here. So this is what a galaxy would look like if it had an age of only 100 million years. This is what happens if I age the galaxy down to 12 billion years. So these are the hot A-type and B-type stars that dominate the light when the galaxy is younger. And when the galaxy gets older, it looks redder. So this is very clearly already tells you that you can measure at least approximately the ages of galaxies just from their spectra. That's the first sort of zero-order parameter you might try to measure. But there's a lot more information there. What you're looking at here is just kind of a lot of things to look at once, but just focus on one panel up here. What you're looking at is the change in the spectrum if I double the abundance of the element nitrogen. So you see 10% changes. These are all molecular features in the spectra of the stars. This is the same thing if I double the abundance of carbon, calcium. The point isn't to look at this in detail, but just to notice that there's information all over the place to measure all these different elements. The same can be said of the iron peak elements, vanadium, chromium, manganese, and so on. They make noticeable effects on the spectrum of galaxies. So the goal is to actually measure these things. Like I said before, you can even imagine measuring the initial mass function, the number of lower to higher mass stars in galaxies, because of these special spectral features that depend on surface gravity or luminosity. What I'm showing here is a ratio between two models that are the same in every sense except for the IMF is different between, there's two different IMFs. And so you see these features that are different, like this sodium feature I showed before, this iron hydride feature, etc. They are varying at the percent level due to changes in the initial mass function. So this is subtle. It's not a huge effect. It's a percent level effect. But it's measurable. It's not zero. And so in principle, you can actually decode what kinds of stars are in galaxies all the way down to the very bottom of the main sequence, even in galaxies where you can never directly resolve those stars. So in a galaxy like M87, which is a nearby massive elliptical galaxy, we will never, ever be able to directly image a faint M dwarf in that galaxy, especially in the central regions. It's too crowded, stars are too faint. So the only way we can hope to measure what kinds of stars are there below the main sequence turnoff is through these indirect techniques. There's all these features here. And again, information is spread all over the place. So this is all the way from the blue optical out to 2.4 microns in the K-band. All right, so that's the information content of the spectra. Before I actually show some results, I wanted to describe why we might bother trying to work so hard to measure all these things. So this, periodic table of the elements, right? Okay, so the thing that we often think of looking at this diagram as astronomers is grouping elements together by where they form, by their formation sites. So for example, I've labeled here in yellow elements that form primarily when massive stars explode, or form from massive stars. So oxygen, neon, silicon, magnesium form when the star is burning hydrostatically, and then calcium, titanium, the heavier elements here, form when the star actually explodes. So these are elements which are returned back into the ISM when type 2 supernova explode. These are stars that explode on short timescales. Another class of elements, these are called the iron peak elements because they are around iron, form when a type 1a supernova explodes. This is the white dwarf that explodes. So these elements are produced when type 1a supernova explode. There are other elements like carbon, nitrogen, fluorine, elements down here, which form primarily in these asymptotic giant branch stars. And then there are other elements, these elements in white, that form this process called the R process that we don't understand. It could be from the merger of two neutron stars. We're not really sure. So the point is, I don't really care about these elements in particular, aside from the fact that they're used to make the Earth and us and so on and so forth. But from astrophysically, why I find them interesting is because you can think of them as a table of clocks. Right? These elements in yellow form on short timescales, whereas the elements in red here form on longer timescales. So these type 1a supernova explode on long timescales. And the AGB stars in blue here, they form and evolve on intermediate timescales. So you've got a bunch of different clocks that should give you interesting probes into how the galaxy assembled. To give you a sense of how this actually works, imagine, well, first, here's why I said it in words a little more quantitatively. These type 2 supernova explode on short timescales, so a few tens of millions of years after a star forms. These asymptotic giant branch stars form on longer timescales, a few 100 million years. And these type 1a supernova explode over a wide range in times, but going all the way to the present time. So imagine I have two different kinds of galaxies. One galaxy that looks like this, and one galaxy that looks like this. So this is like it would be like the rate of star formation in two different galaxies. So if I'm a galaxy and I form, if I'm just a pristine ball of gas and I start forming stars, initially those stars will be metal-free. The more massive stars there will explode, and they will enrich the ISM with these alpha elements. Then when the second generation of stars forms, it'll form out of that alpha-rich material. Those stars, the massive stars, will explode, and so on and so forth. But the low-mass stars that will live for a Hubble time, they'll live for a long time, they're going to be forming out of more and more alpha-rich material. So that when the star formation stops, before these other things can happen, the stars that are left, those low-mass stars that live for a long time, will have formed out of very alpha-enriched material, and so they'll be very, what we call alpha-enhanced. Contrast that with a galaxy that looks like a star formation history that looks like this. It's kind of just forms a lot of stars over a long time scale. Well, eventually it will form stars, and eventually those AGB stars will start dying and returning carbon and nitrogen and so on back to the ISM, and subsequent generations of stars will form out of that material. And eventually, on longer time scales, the iron that comes from the Type 1a supernova will be ejected back into the ISM, and later stars will form out of that material. So over time, the stars will form out of more and more iron-rich material. So this is the sense in which these abundance patterns provides insights into the formation history, which is what we refer to as extragalactic archaeology. Because you use the present-day abundance patterns of stars to learn about what happened in the far past. And just to show this is not all totally crazy, this is what you observe for individual stars in the Milky Way. This is the magnesium over iron. This is like an alpha element, and this is an iron, obviously. And this is titanium, another alpha element over iron as a function of the iron abundance. These are individual stars in the Milky Way. And the way this is often interpreted is that, the galaxy started out somewhere over here, very metal poor, because the initial gas from the Big Bang was, metal free. You start out over here, and you start out with very high alpha to iron ratios, as I described in the previous diagram. And then over time, when the metal city keeps increasing because stars keep forming and dying, eventually over time, those Type 1a stars start exploding and producing iron, and they drive this ratio down. So it's believed that this whole sort of, this whole shape here is governed by the process I described here. And that when exactly this turnover happens, how high this is up here is all determined by the shapes of these curves to first approximation. So you can use the shape of this to actually read off the star formation history of the Milky Way galaxy without having to sort of look, wind back history or something. And then people actually build fancy models that incorporates what I described in the previous slides to try to fit the data and to make inferences about how the disk of the Milky Way formed over time. So this has been done for a long time in the Milky Way. This is a whole thriving industry. What we're going to do for more distant galaxies where we don't resolve individual stars is take basically all these stars and average them together. That's all we get when we look at a distant galaxy, is sort of the average of the population. So it's obviously a lot less information, but we hope to nonetheless make some progress. All right, so that was all background and sort of overview of the concepts and the tools we use. Now I want to describe a few of the results that we and others have obtained applying these types of models. So again, this is the kind of galaxy that we're interested in understanding, these elliptical dead galaxies. They're very spherical, they're red because they have no ongoing stars, and they lie in that sweet spot of the diagram. So we're analyzing just the optical spectra for galaxies that are old. Just a little bit of detail, we have a bunch of different galaxies that were taken with the Keck telescope. We also analyzed galaxies from the Sloan Digital Sky Survey. We have now a very sophisticated, fancy fitting technique that has many free parameters. The data quality are extremely high, very high signal to noise, etc. To give you a sense of how an actual fit to a spectrum looks, or what it looks like, this is a stacked spectrum of galaxies from the Sloan Digital Sky Survey in black, and the best fitting model is in red. And so you can see just kind of by eye that the fit is pretty good. And then down here are the residuals. So the fit's about good to 0.25%. But remember that each one of these features you see here is actually a blend of many dozens or even hundreds of individual lines. So it's a somewhat non-trivial thing to get this all to work out right. So the fit looks good, that's fine. But you actually want to understand what you're kind of getting at the end of the day. So this is one thing that we've measured from these spectra that was sort of a bit of a surprise at the time. And this was that the initial mass function that I mentioned before, so the relative numbers of low and high mass stars, appears to be different in different kinds of galaxies. So what's shown on the y-axis here is just some fancy way of plotting the initial mass function, where in the Milky Way we live at this value right here, and it turns out that this value increases as you go to higher and higher mass or higher velocity dispersion galaxies, and or as you go to galaxies that have higher values of this alpha to iron parameter. So up until this point, there wasn't, we didn't really have a good sense of what the IMF was in other galaxies. We thought it might be just constant, but it turns out that at the factor of 2 or 3 level, these more massive galaxies appear to have these very different initial mass functions. This is a very active area of research now. and it's still an open question as exactly what are the physics that's driving this variation. At the same time, it's been known for a while, this is just some example from our own work, that the whole sort of chemical makeup of the stars and galaxies varies in an interesting and systematic way as you go to more massive systems. So this is the abundance patterns of these various alpha atoms as a function of, again, the velocity dispersion of the galaxy. But you can think of this as basically as the mass. Some more massive galaxies are up here. And as you go up in mass, certain elements, like oxygen and magnesium, are increasing very rapidly as you go to the most massive systems. And that's consistent with that picture I showed you before, where this is a sequence of galaxies that have shorter and shorter star formation timescales. There's an interesting structure here, though, where the heavier alpha elements are flatter, and we think we understand that it's just a consequence of how type 1a supernovae explode. There's another interesting structure that we didn't expect to find, which is that, this is a little bit of a side point, but the abundance of this funny element cobalt actually seems to track the abundance of oxygen. So this is the data here. They track each other in a one-to-one line. And as a student who's been building some of these chemical evolution models, and there's the offset, there's a significant offset, but the fact is the models produce a similar trend as well. And it turns out this, again, is a simple consequence of how type 1a supernovae explode. So you can actually use the abundance properties of distant galaxies to learn something about the physics of type 1a and type 2 supernova. Because there are other, this is just for a particular kind of model for how stars explode. Other kinds of models don't produce the same trend. So it's an interesting constraint on how stars explode. So again, this can be interpreted just in terms of a timescale of star formation. To put it in a nice cartoon, which Daniel Thomas did about a decade ago, this is the current picture for how we think these elliptical galaxies formed. And you can just focus on the top panel or the bottom. They're basically the same for these purposes. What's being plotted here is basically this. It's technically the specific star formation rate, but just think about it as the rate of star formation, as a function of look-back time. So the universe is going this way in time, and the schematic diagrams that explain all that data and other data that we've collected as well, others have collected, is that the most massive galaxies seem to form their stars on very short timescales and at very high redshift, and then they stop forming stars and they just sit there, sort of what we call passively evolving, sort of doing nothing for most of the age of the universe. And the lower and lower mass galaxies form their stars preferentially at later times and over longer timescales. So you see the width of these Gaussians is growing with time, and that's used to explain why the abundance patterns varies in systematic ways with galaxy mass. So this is very surprising. This is something that nobody really expected, I think, and it's given all kinds of funny names like anti-hierarchical growth and downsizing, and whenever we don't understand something, we just give it a silly name. But the fact of the matter is, it's very bizarre that these gigantic galaxies, the most massive galaxies in the universe, seem to have formed their stars over a few 100 million years and then stopped. And that's remarkable for a few reasons. It's remarkable, it's not quite clear how that even happens to begin with. But then why, when it's sitting there, sort of on its own in a dark matter halo, being pummeled by different kinds of galaxies that are accreting onto it over time, like in the movie I showed, why it would preserve the appearance of being old and having formed on a short time scale. So why doesn't that messiness of hierarchical assembly not mess this all up is another outstanding issue. But this is the current sort of schematic toy model we have in our minds for how these elliptical galaxies formed. And it's still not being reproduced generically in any cosmological simulation of galaxy formation. So this is the kind of constraint that comes out of the data, but it hasn't really been able to be reproduced by even the state-of-the-art simulations. So the way of summarizing what we've learned so far, this is sort of a beautiful plot of the abundance of basically every atomic numbered element up to 80 something or other, as measured from the sun. This is a review by Martin Asplund. This is sort of a heroic effort and one of the modern successes of stellar astrophysics, that we can chart the abundance of basically every element in the sun. And we're not quite there. This is based on extremely high quality data. We're not quite there yet with galaxies, but we're making a lot of progress. Right? We're able now to measure the elements going from carbon, nitrogen, and oxygen up to the iron peak elements and beyond. And we're learning, and this is telling us sort of fundamental insights into how galaxies are assembling over time, how they're forming their stars and how they're assembling. So in the last few minutes, I want to just highlight work that's being done at higher redshift. This is work that was led by a graduate student here, Jian Choi. So all the work I described up to now was galaxies that are at redshift 0 at the present epoch. So it's true archaeology. Use the present-day properties to learn about the past. So now we want to actually go a little bit further back in time and learn something about what galaxies were like at redshift of a half, or redshift 1, and see if this picture that I showed you before actually holds together. So this is a bunch of different galaxies drawn from a survey called the AGES survey, which was data taken by the MMT, which is a telescope that's operated partly here by the CfA. These are galaxies out from redshift 0.1 out to redshift 0.8 or so. That's about half the age of the universe is redshift 0.7. And we select just galaxies that are these dead quiescent galaxies with little or no star formation. This is star formation rate versus mass. These are the quiescent galaxies. And again, you can stack the spectra together, and you can make these comparison between the data and the models, and overall the models fit the data very well. And one of the things you get out is you can measure the ages of the galaxies, you can measure the ages of the stars. That's what's shown here, the age of the galaxy as a function of redshift. And these lines here are basically proportional to the age of the universe. And what you can see is the more massive galaxies, like these green lines here in the blue, the stars are aging just as if they were just doing nothing but aging along with the age of the universe. And that's what we mean by when we say like a galaxy is passively evolving. It means that the stars formed at some time, and they're just sitting there doing nothing but evolving according to the clock, which is the age of the universe. So these, and down here, there's not that much data, so we can't quite say, but the more massive galaxies are consistent with just sitting there doing nothing over the past half the age of the universe. And again, that's consistent with the schematic diagram I drew before, which is that these galaxies form their stars very early, and they sit there doing nothing. Now, for various reasons, ages are actually kind of hard to measure in practice, and so we have another diagnostic, which is these element patterns. These are a little more stable and easier to measure. And in fact, this is now, I flipped the axes around. This is age as a function of mass, and then the different points are different redshifts. And this magnesium over iron versus mass, again, for different redshifts. And aside from two outlying data points, there's basically no evidence for any evolution in this quantity with time, which again is exactly what you would expect if galaxies just form their stars and then they're doing nothing. What would happen is that they would age, the stars would age, but the elemental abundances in the photospheres of stars wouldn't change because the stars are just sitting there doing nothing. This is exactly what you would expect. So this is kind of a combination of look-back studies of galaxies and the archaeology at the same time. And the data are basically consistent with these galaxies just sitting there doing nothing for a long, long time. Now, so you might ask, well, how does this jive at all with the movie that I showed at the beginning? And the reason is a somewhat technical one, but the point is that the data from these galaxies were collected in the inner central regions of the galaxy, not the entire galaxy. And what we think actually happens is that the galaxies grow in what's called inside out, which means that the central regions are in place at early times, but the accumulation of material from mergers and accretion builds up the galaxy in the outer regions, kind of like an onion layer over time. And so while the inner regions seem to be doing nothing but sitting there passively, evolving, the outskirts are probably growing over time. This is hard to measure with current instrumentation because you need to collect spectra of galaxies at large radius, but it's something that we're pursuing now. Okay, so that's all I wanted to say. The first summary point is that the stellar populations of galaxies provide fundamental insights into how galaxies form and evolve over time. And in fact, it provides really, aside from the structural properties, it provides one of the only real clues we have, at least in the optical spectral region, for what's happening with galaxies. So it's really a fundamental tool to understand how galaxies came to be. Now, in reality, the construction of models to interpret the light is complicated by a variety of realities, and that includes the fact that a lot of stellar evolution is actually not very well understood. I think a lot of, at least when I was a grad student, it was kind of presented as if it was a solved problem. But I think it's clear to people who've been working in the field for a long time, and increasingly clear to even people who work with galaxies, that this is a major problem for making progress in the extragalactic community. So there's an increasing amount of crosstalk lately between folks who study stars and folks who study galaxies, which is pretty interesting, I think. The spectra of stars is quite uncertain and difficult to model, especially for cool stars. This is an old problem and one that's very actively being pursued by a number of people, including people at the CfA. And the entire problem is very complicated by the fact that you have this massive deconvolution problem in many different senses. In that sense I showed earlier of the resolution, the fact that you'd like this ultra-high resolution spectrum of stars without the Doppler motions blurring things up, but you can't get that. And also the fact that the star formation history and the chemical history of galaxies tends to make things rather more complicated. So it's a very challenging problem that we've been using, borrowing a number of tools from computer science and statistics to try to unravel a lot of what's going on with the data. But the upshot that seems to be robust to all these sort of more woeful parts is that the data suggests this picture where the central regions of massive galaxies are very special places in the universe. They're places that don't have any analogs in the nearby universe. There's no analog in the Milky Way as far as we can tell. They seem to have formed very rapidly, and then basically for some reason we don't understand, seem to have just sat there passively evolving for most of the age of the universe. Okay, thanks for listening.
We'll take questions for a few minutes.
How does an AGN factor into these galaxies, specifically the ones that form stars, massive amounts of stars in a short time period?
Yeah, that's a great question. So I'd say that the current conventional wisdom is that the AGN were a key component in turning these galaxies off, so turning the star formation off, and then keeping them off for a Hubble time. Because what's fascinating about these massive galaxies is that they have no ongoing star formation, in spite of the fact that they're surrounded by gas that in principle could cool on a Hubble time, or shorter than a Hubble time, and collapse and form more stars. And so another major puzzle in this whole field is why is that gas not cooling and forming stars? And one of the main interpretations or main explanations is that the AGN is occasionally turning on and heating the gas around it to keep that gas hot and not keeping it from cooling and forming stars. So it's believed that the AGN actually plays a critical role in these massive galaxies.
Well, if there are no other questions, let's thank our speaker again. And next week we'll be hearing from Nia and Mara on stellar nurseries.